do it in 40.
Good luck. 40 milliseconds.
Yeah. Can I stand here on the bottom? Okay, it's closer. Okay, so thank you for joining today. My name is Maoz, and I'm leading the US business for Anodot. And Anodot is a company that delivers real-time business incident detection using anomaly detection. And today I will talk about anomaly detection. What is it? Why do you need it? And what are the steps to implement anomaly detection and achieve real-time business incident detection? But before that, let's talk about the problem. What is the problem? And the problem that we are talking about is real-time business incident detection. And it's talking about the fact that companies collect today a lot of data in a lot of different verticals, you will see that. But then they have challenge in translating this data to insights in real time. And they lose millions of dollars because of incident that happens, and they discover them after hours or after days or even after weeks. And we can look at some use cases. So if you are looking on different industries or different verticals, and let's say you are in the online payment and loans, and you are having a lot of millions of different transactions that happening across different partners, mobile devices, geographies, type and loans, or in the edtech space where you have a lot of data and you are tracking revenue, conversion, impression, and you are tracking that across multiple publisher, advertiser, campaigns, and the list goes on, e-commerce, ride-sharing, and even IoT space where you are tracking a lot of data around temperature and RPM and across different machines, different components. So really, the common thing for all of that is finding the needle in the haystack. You mentioned that before. And let's look at one or two more examples in details. So basically, find the needle in the haystack, like I said. And this is a quote from Pedro Silva, who is Senior Product Manager in Credit Karma, and one of Anodot customers. They're talking about the fact that if the entire service were done, we would know pretty quickly, of course, but for errors impacting only specific page, offer, browser, or platform, all of which affect revenue and customer satisfaction, we would not know for at least a day or two. And these are two more examples, one from the edtech space, where a company that is actually doing a spend of advertising money for their customers, and they had some bug in their code, and for 10 hours they were actually spending wrong the budget that the company gave them to spend, and they had a loss of $300,000 for a problem that happened, and they could have discovered in the first minute, but because they didn't have the right solution in place, it was discovered after 10 hours. And last example is a fintech broken payment API where company people were not able to execute transaction because of some API that was broken. And this goes on, we see a lot of different use cases. Now, you might say, you know, there are many BI tools. I implemented a lot of dashboard tools, reporting, and so on. So I'm good at that, and I don't have any issue, and anything that will happen, I will discover right away. But basically, there are challenges in that approach, and the challenges are several. So first of all, in today's world, you have millions of metrics, and we'll see that in more details later on. But basically, even if you are tracking impression and clicks in the advertisement space, and you are tracking that across multiple publisher, advertiser campaigns, you get very quickly to hundreds of thousands and millions of metrics that you need to track. And you cannot track all of that in dashboard or report. So you cannot look on, put an army of people to stare at dashboard and report and try to understand what is going on. So usually what companies will do, they will focus only on the high level, and then they will miss a lot of important insight in the lower level. Also, for the metrics that you do track, you have a lot of maintenance and unautomated process because you still need to create this dashboard and reports. A lot of false alert, either positive or negative, because it's very hard to know what is the normal behavior and what is not normal behavior. And at the end of the day, you will end yourself in a situation like that in the traditional monitoring, where you stare in multiple dashboards and get a lot of alerts and trying to understand what is going on. So this is the problem, and we explained the problem space and how do you not get the solution for that. And how do you gain real-time business insight? And the answer is using automated anomaly detection. And first of all, what is automated anomaly detection? We're talking about using advanced machine learning techniques to learn your data's normal behavior, identify abnormal behavior, and alert on that. And next, what I will do, I will actually talk about what are the steps to implement such a solution. And we are talking about 5 steps: metric collection, normal behavioral learning, abnormal behavioral learning, behavioral topology learning, and feedback loop. So a lot of learning. And before I'm drilling into the details, this is a kind of exercise for all of you, not for now. We have a booth in the exhibition area with a very big poster of Find the Anomaly, and one of these is different. So I'm challenging you to come later on and say, where is the anomalous penguin? Okay. Now, let's talk about the first step. So the first step is metric collection. And in metric collection, we are talking about several points. We're talking about universal, scale to millions of metric, and granular. And universal means that you want to have a system that will be able to collect data from any type of source. I show different verticals, but also in the same verticals, you want to collect data from business, from IT, from different departments, and so on. So you want to have a system that will be able to actually consolidate everything and show you what is going on in the context. This is the one thing. The second is the granularity, and let's understand why granularity is a must. And granularity is the point where you want to be able to find anomalies, even if the anomaly happens in a specific browser or specific OS device or specific geographies. And why granularity is a must and why you actually scale to millions of metrics, because this example is talking about I'm in e-commerce and I'm tracking 2 metrics, number of purchases and revenue, only 2 metrics. And I see that a lot. I'm talking with customers and I'm telling me I have only 10 metrics, but then I'm asking, okay, but do you want to know when the problem happened only in a specific product? Yes, the answer is yes. And do you want to know only when it happened in a specific state? And still the answer is yes. And it's going on and on. And basically, if you summarize the total number of metrics that you will have for this permutation, now I will test, like I saw that everyone here are chief data scientists and very smart people. So how many metrics we will have here? Anyone? Okay. You saved the day. So 400,000 metrics, and this is only for 2 metrics that we are tracking. So it's very important to have the ability to drill down to each of these permutations and to be able to find anomalies on each of these permutations. And this brings us to the next slide of having a system that will be scalable and will support millions of different time series metrics. And this is a picture from Anodot architecture. And just to illustrate the amount of data that we deal with on a daily basis, so 5.4 billion daily samples, 120 million time series metrics, and the list goes on, and it grows every day in a very fast rate. So this is the metric collection. Now we collected the data. What do you want to do with the data? And by the way, I'm talking about a collection of data on streaming, meaning that you want to have a system that will actually do all the calculation on the stream. Otherwise, your detection will not be real time. So you want to be able to run everything in real time on a stream of data. So the stream of data is flowing with millions of metrics. And then what we don't want to do is to learn the normal behavior. And why do we want to learn the normal behavior? So when something abnormal happens, we will be able to detect that and alert on that in real time. And this example is showing a graph from Anodot system, and you can see how anomaly-based alert will find the problems hours before the static one. Everyone knows static threshold, and that you try to find like where do you want to put the static threshold, and you don't want to set it too high or too low, and it's very challenging to do that. So a lot of time, again, companies will compromise, and then the line, the red line that you see, the break one, this is the static threshold. So once an anomaly will happen, it will alert only when it reached to this static threshold. But because anomaly detection platform will actually analyze the normal behavior very accurately, then you will know about the problem at 1 p.m. Now, Learning of the normal behavior is something that, by the way, there is a shaded area here. I don't know if it's if you can see that, but if you see there is a shaded area that presents the baseline that the system actually should learn. Now, learning of the normal behavior is something that is very challenging. It's not an easy task, and you need to take a lot of factors into account. And I will go about some of the factors that you need to take into account. So seasonal patterns, signal types, and adapt to changes. And we'll explain about each of those in a short. So seasonal pattern, talking about the fact that you have seasonality. And every industry that you will go to, there will be some seasonality. And seasonality is talking about the fact that the behavior of the data will not be the same if you are looking on different times of the days, different days of the week, weekend versus weekdays, and so on. And let's take, for example, e-commerce. When you have purchases of products, you will see seasonality that you will have more purchases, let's say, in the evening where people are back from work, and you will see less purchases in the noon when people are at work, and so on, or weekend versus weekdays. And you need to have a system that will actually understand that this is the seasonal behavior. It will understand that this is the actual normal behavior, and will not alert whenever you have a peak in the weekend and say this is an anomaly, because this will be a noise. So this is, here for example, you can see that we have like multiple seasonality. We have daily seasonality and weekly seasonality. Second part, learning the normal behavior. Not all metrics are created equal. So basically, this is talking about the fact that you have different behaviors of the signals. You will have a behavior like smooth, like we see here, that is very seasonal and very clear behavior. On the other hand, you will have irregular sampling, like we see here, multimodal, sparse, discrete, step. And if you have a system that knows to deal only with one of the signal type, where mostly what we see that the companies that try to build it by themselves, they will focus mostly on smooth behavior, then it will not be good enough, because then the learning of smooth behavior might be okay, but all the rest of the signals will not be learned in a good way, and actually you will start to get alerts on things that are actually the normal behavior. And so what do you want to have? You want to have a system that actually what it will do, it will have multiple algorithms, and in the stream itself, it will actually classify signal to the right category, and then match it with the right baseline distribution and algorithm, so the learning will be very accurate no matter which signal type you are looking at. And why is it important? We did an analysis based on 20 million metrics that we had at the time in the system about what is the distribution of the signals. And we saw that smooth behavior is indeed very meaningful. It's 38%. But if you are using a system that that knows to deal only with smooth behavior, it means that you are missing 62%, which is distributed between the different signal types. And we even went one level lower, and we did this analysis per industry, and we are looking on edtech and e-commerce, and we actually found something interesting. We saw that in the e-commerce space, we have much more irregular sampling, and our explanation to that was that in e-commerce, it's much more based on human behavior, and people are entering the website, exiting, and then it's much more irregular than in the edtech industry, where it's much more based on machines. Okay, and the last thing, adapt to changes. So you need to be able to adapt to changes. Changes happen all the time. You add capacity to server, or you add some promotion, and now you have like different level of purchases. And you need to be able, you need to have a system that will understand after some time that something is anomalous, but maybe this is now the new normal behavior, and I need to adapt myself. I need to adapt the baseline to the new normal behavior. Otherwise, the anomalies will keep open and will never be closed. So this is what we see here, where at some point of time we actually adapt to the new session. Just look, what's the time? Okay. Okay, so now we talked about metric collection, we talked about normal behavior learning. Let's see a few examples, and this is an example from real customers at Anodot. So this is an example of an e-commerce, and you can see here this specifically looking on source of Google Analytics, and you can see that we are looking on average session length, and you can see how the system actually learned the normal behavior over time, and at some point of time it discovered an anomaly here that actually means that there is a drop in session length that happened for a specific brand, was discovered after 1 day, but actually happened for 5 days. This is like after the fact in this example. Other example, security. Getting back to Anodot, we are not focused on security, but a lot of time we have customers using us also for security use cases. So this is an interesting example. This is actually looking on the number of attempts with fake emails that happen on a website. And always when people are trying to enter a website, they will do sometimes mistake on the email. But when you have a peak like that, then you understand that this is an attack. Another security in bot detection, ad network. I'm not going over all this example. This is a peak that you see, and you can see here the seasonal behavior. How we discover like a peak here that say that there is a peak in the higher response time for specific DSP. Gaming industry, a peak in new install, and the list goes on and on. So next, abnormal behavior learning. So abnormal behavior learning is talking about reduction of noise. Any system that you will use for anomaly detection will have a lot of anomalies. Now, it doesn't mean that all the anomalies are important. Some of them will be less important, some of them will be more important, and you want to have a system with an ability to actually score and focus you on only on the important anomalies. So what we are talking about in these steps is actually giving a score to each anomaly. So basically, you have a lot of anomalies. You want now to do something that is called second-level learning, which is actually learning the behavior of the anomalies themselves, and then give them a score between 0 to 100, which represent how significant is the anomaly, how important it is, so you can focus only on the important anomalies and ignore all the anomalies that are not important. And the scoring can be done with multiple ways. Some of them will be to, for example, look on the height of the anomaly, like is it a deviation of 5% or 50%? Look on the width of the anomaly. Did it happen for 5 minutes and then got back to normal behavior and then who cares? Or is it something that happened for 2 hours? And so on. So this is the scoring, and the scoring is very important to reduce noise in the system. The next step is behavioral topology learning, and this is a very important step. Before I will talk about what does it mean, I will go to this guy, Dr. Maoz, which I guess that you all know. So this guy at the show, and the show talked about is some crazy doctor, and every episode someone come to the hospital, and he has a lot of different symptoms, and then this guy sit with his team, and starting to write all the symptoms on the board and trying to understand what is actually happening and what is the disease. And usually his team comes with an answer. What is the answer that usually the team will say? Who knows? So the team will say it's lupus, and then he will say it's not lupus. Okay? So practically all the team job in the episode is to say it's lupus. Okay? So and then he goes to somewhere else, and suddenly he has like a kind of a light bulb, and he knows what the problem, and he understands the root cause, and he goes, and the patient leaves till the next episode. Okay, and this is talking about from univariant to multivariant, and basically, it's talking about correlation. So all the things that we talked about till now are actually single metric anomalies. So we did the analysis on each of the single metrics. But now if there is a problem And like we see here, we get a lot of alerts on each one of these problems. It's very hard to know what is the real root cause analysis. So what you want to do in this step is to move from the univariate to multivariate and actually do correlation between all the metrics and understand and send an alert that will focus only on the important metrics that are part of the problem space. So going back to this example from Anodot, so basically what we do here, we actually analyze across all the different metrics, and you might send like 1 million metrics and more, and the system in that example will actually find the correlation and will actually alert about the problem in context. So in this problem here, what we see is that we have a drop in the payment completed for specific payment provider ID. And we can see with the correlation that we understand the root cause, because we see that at the same time there is an API error peak for payment type ID number 2. So you actually get a story that tells you what the problem is. And this is very important, otherwise it's very hard to understand the root cause. I see this guy standing, so I'm starting to feel that the end of the time is approaching.
You still have 1 minute.
Okay, 1 minute. Okay, so very quickly about this, we talked about all these 4 steps, and one note, you want all these steps to be unsupervised. You don't want to start to define models, rules, and things like that. Just push data and get results. The 5th step is talking about feedback loop. You always want to have like an ability for the user to close the loop. Not necessarily you want to rely on that, but you want to be able to have the ability to actually say, this is a good catch or it's not interesting, and actually give feedback to the system. And I'm finishing in 2 minutes. So reducing the noise, we talked about all of the steps, normal behavior learning, abnormal behavior learning, topology learning, and so on. And this is, again, an example from anomalies that happen in Anodot system in a given week. And you can see how we reduced the noise from 80 million metrics that we measure on a given week. We had 200,000 anomalies, which is you know, if we would have sent 200,000 alerts to our customer, then it wasn't a good situation. But then at the end, after everything, we end up with 2,000 correlated incidents across all the customers. Last slide. So I hope this presentation was educational. Again, we learned about some notion of anomaly detection, what you can do with that, and how you implement anomaly detection. At Anodot, again, getting back to Anodot, we actually implemented such system which is completely unsupervised, and we have a lot of success. We have today like customers which are really big and really small. You see some names like Google and Microsoft and Credit Karma and so on. So I encourage you to come to the booth and to hear more about Anodot. Thank you. Right on time.
Awesome. I personally found it also very informative for myself. I have just one more. I heard from the gentleman there that the questions, if you and also the future speakers could repeat fully.
Okay.
So it goes into the system for
Okay.
their recording eventually.
Okay.
So just repeat every question they ask, and we can take 5, 6 questions. So you can start right from there. If you could speak up a little bit.
Okay. Right, yeah.
As anomalies, but for some of them you would like to provide alert, so something wrong, and for other guys you go, okay, it's a very good.
Yeah. Okay. So the question is, I'm repeating. So you see, I'm following your instructions. So the question is how you can identify between good anomalies and bad anomalies, because, and we see that because sometimes you might have anomalies of a peak that you will say, this is good. Okay, let's say it's revenue, and there is a peak in revenue, it's good. But let's say, again, it's a number of errors, and suddenly I have a peak, it's not good. So you need to have a way to identify. So basically, how we do that in Anodot, at Anodot we will generate anomalies from everything. Okay, so basically good anomaly and bad anomaly might get the same score, but the user has another filter which I didn't talk about, which is alert. So basically we'll be able to define an alert later on across all the different anomalies and say, it's kind of a tuning and say, for this metrics of revenue, I want to get only the good alert, so I want to get only the bad alert. So it will be able to define kind of direction. Okay? It's not supervised, it's unsupervised, but later on the user adds some filter. Otherwise, you don't want to flood him with alerts.
So my question is, how will you move from detecting anomalies to predicting an anomaly? And I'm asking from the point of view of, you briefly mentioned IoT systems. And since you're trying to predict when something is going to fail, if I predict half an hour before it, because that's
Yeah, so the question is how you move from finding anomalies, because finding anomalies is actually finding when it's happened, versus prediction. Now, my answer is that anomaly detection by its nature, it's already predictive, because, and there was a question, it was a question specific to IoT and how you do predictive maintenance. So we have examples of customers in the IoT space that basically we are able to predict malfunctions. For example, because you will start see, it's like when you are sick, getting back to Dr. House, something you start feeling, not well, and then it comes later. So also in the machine, you will start seeing like peaking the temperature. Suddenly there will be a drop in, for example, we are working with some printing company. Suddenly there will be a drop in the number of pages printed per minute and things like that. And the malfunction will come later. So by the nature of anomaly detection and by focusing on very granular information, you will be able to actually find the problem before it actually become real problem. So this is one part of my answer. The second part is that this is also something that we are working on adding prediction according to the time series behavior that we have. Okay? Yeah. Yeah, so basically this is based on all the different algorithms that, repeating the question, yeah, sorry. So it's a very common question of in the learning space, how do we make sure that we don't learn abnormal behavior as normal behavior? And basically this comes, we saw cases of customers that tried to develop something by themselves, and then the process that they had was they gave data to their users and they said, mark me the anomalies, and then they took that back to their models and ran that and again gave it to the customer, and it's very kind of supervised process. And we are doing that. I cannot give now all the details of how we do that in the algorithm, but the algorithm we developed actually knows to identify over time what is an anomalous behavior, what is not anomalous behavior, and actually ignore this anomalous behavior in the learning. And we can talk later and we can give more details.
You have another question on that?
Yeah, sorry. On what, sorry?
Unmanaged data sets, so anomaly happens less than 1% of the time, and you're trying to predict it, and it leads to a lot of false positives.
Okay.
Have you had some experience or some case that you have?
So basically the approach that we take is a bit different, because we will find on the anomalies that happen, but we will, like I said, we'll give a score to each anomaly. And then basically later on the user can come and say, like, I want to be alerted, I am in charge to revenue, and I want to be alerted on everything happening in revenue, but send me only anomalies that have significant score higher than 70, and so on. So this will actually help to reduce noise in the system. This is the approach that we take. So it's kind of completely unsupervised till the point of the anomaly that happened, and then later on the user will say, like, in high level what he wants to be alerted on. Okay?
All right.
I think there was someone
okay,
there.
just one really quick.
You mentioned that retaining granularity is key.
Yeah.
You go down to the most granular levels. How do you deal with sparse times?
So you know, the granularity doesn't mean that you send now till the bottom level of the granularity. So we have an algorithm to deal with sparse. We can deal with sparse as well, but also there is some level that it doesn't make sense to go deeper. So for example, we had a customer that started to send the data in the level of a different ad size. And then he said, okay, you know what, it's too much. I don't want to do that, and he went one level up. So even in the business aspect, it's not always it makes sense to go to the most granular. So usually it will go to some level of granularity, and then we have the algorithm for sparse that know to deal with sparse data.
Okay,
Thank you.
Awesome. Thank you very much, Uri. Awesome. Thank you.